Hello, my name is Rachel Siegel. I am a second-year master's student in the Civil and Environmental Engineering program at the University of Vermont and the graduate researcher for this project. We are studying bridge stream network modeling for bridge risk assessment and flood mitigation. To start, I'll give you some background for the project. Tropical Storm Irene came through Vermont in late August 2011. The storm deposited an average of 3 to 5 inches of rain, and in some places as much as 8 inches. Irene is only superseded by the flood of 1928, and many locations in Vermont even surpassed that event. With the storm came severe flooding, causing damages or failure to as much as 500 miles of road, 300 bridges, and 200 miles of state-owned rail in Vermont alone. The northeastern United States is experiencing more frequent and extreme precipitation, creating more flood events. This has led to stakeholders asking questions about future and current projects. So how durable is transportation infrastructure under transient conditions, and how might changes in infrastructure affect other projects further up and downstream? In this work, we are attempting to quantify these bridge stream network interactions under transient conditions to create a framework for risk assessment and flood mitigation. To observe a broad variety of these interactions, we selected 3 different river reaches to capture sections of low, medium, and high gradients. The first is the Otter Creek, which features a very low gradient river with multiple road bridges as well as rail line and over 100 culverts. The second is a small section of the Black Creek, which was selected to represent a more medium gradient. This section has 5 bridges, 2 of which are rail bridges and no longer in use. However, this section does feature a popular rail trail that is used by the public during all seasons. The Mad River was selected for the medium and very high gradient sections and also features 16 road bridges. So each one of these rivers is modeled in a 2D unsteady HEC RAS model and calibrated to Tropical Storm Irene, as well as several other events, including 25, 50, and 100-year storm events. Below, you can see the Otter Creek featured on the left and the Mad River on the right. Both of these photos are showing each river with their modeled transportation infrastructure and their respective inundation boundary for Tropical Storm Irene. You can see how the Otter Creek is much longer and has a very large floodplain, allowing the water to spread, whereas the Mad River is shorter and is less connected to its floodplain, leaving the water more constricted. These calibrations are verified through USGS stream gauges and photographed high water marks to ensure reliable hydraulic models. Field work is also being done at the upstream Mad River location to create a depth discharge rating curve. Using this developed curve, we can calibrate the Mad River model to other storm events, such as the Halloween flood that took place in 2019. Each river is evaluated for multiple storm events and observed at points of interest. So in the middle here, you can see a map featuring the Waitsfield covered bridge. This historic bridge is one of the oldest in Vermont and was overtopped as well as damaged during Tropical Storm Irene. What's interesting about this location is that when the simulations are run in HEC RAS, you can see that all of the inundation boundaries for the varying storm events are very close together and in some case overlapping. And this could suggest that this bridge would be overtopped for less severe storms as well. However, when you look at their corresponding hydrographs in the bottom right, you can see a dramatic difference in the volume of water of Irene compared to the smaller events. This shows how sections of the Mad River that are disconnected to its floodplain forces the volume of water to flow at greater velocities, potentially increasing scour and creating other hazards. So once these initial models are built, we then begin adjusting the structure. So for example, we might remove bridges, raise bridge elevation, expand widths, and so on. This is to simulate varying projects stakeholders might have along the river. And with these alterations, we run the models again and observe changes up and downstream. So once again, we extracted some of the HEC RAS results at the Waitsfield covered bridge. Here you can see what the current conditions are for stream power in the top left and velocity in the top right, with the bridge in place during Tropical Storm Irene. In this scenario, stream power and velocity are highly concentrated at the bridge location, and these values are much lower up and downstream of the bridge. But once the bridge is removed, you can see how much this changes. Stream power in the bottom left and velocity in the bottom right increase up and downstream throughout this section of the river corridor and not just in the bridge location. This network sensitivity can pose a risk for other structures further downstream, potentially increasing their velocity and stream power there as well. This might lead to increased scour. It could change the direction of flow and create a higher risk of overtopping or even flooding in some of these areas. So with this work, we hope to incorporate an optimization wrapper that is being developed in another project. This wrapper will allow us to run many simulations and expedite some of the result outputs. The results across all three rivers will then be compared to frame a simplified risk assessment. And so by identifying similar sensitivities within the bridge stream networks, we hope they can be applied to other river reaches with similar geographic and climatic conditions. And with that, I'd like to thank the Transportation Infrastructure Durability Center at the University of Maine for their financial support and the Vermont Agency of Transportation for their matching contribution and valuable feedback in this research, as well as others from the University of Vermont for their help in fieldwork and model calibration. Thank you very much.